many times a day, this would allow small, reusable shuttles to catch up with it. Of course, it's not that easy. At its lowest point, the tether's tip is dashing through the atmosphere at around 20,000 kilometers per hour. Because of Earth's atmosphere, we can't lower the skyhook too much, or it will get too hot from air friction. So it will dip to a height of 80 to 150 kilometers and no lower. To match this, we'll need specialized spacecraft that can get to the tether. While this isn't exactly easy, it's still much cheaper than getting a big tin can filled with rocket fuel to go 40,000 kilometers an hour. Catching the tip will be a challenge too. There's only a short time window of 60 to 90 seconds to find a tiny thing in the sky moving at Mach 12. To make this easier, the tip could have a sort of fishing line, a kilometer long, with a navigation drone that helps the spacecraft connect. Another challenge is keeping our skyhook in orbit. As more and more ships latch onto it and pull themselves up, they use up the momentum that keeps it in place. If we don't do anything, it will slow down and crash into the atmosphere. And here, we can cheat the universe a bit. The skyhook is a battery of orbital energy. It's possible to balance the payloads coming in and being sent off. Arriving ships bringing humans and materials home to Earth add energy to the tether, which it can give to other ships departing into space. This way, the tether doesn't lose any energy. The more we use it, the cheaper it gets. If we're still losing energy with each boost, we can recover it with small electric or chemical engines that regularly correct the tether's position. A set of tethers, one around Earth and one around Mars, could make trips between the planets fast, straightforward, and low cost compared to rockets. The Earth tether would sit in low Earth orbit to grab people and payloads and fling them off to Mars. The Mars tether catches them and slows them down for a landing on the surface. In the opposite direction, the tether could pick up a vehicle traveling through Mars's thin atmosphere at only about 1,000 kilometers an hour, not much faster than our airliners on Earth, and fling it back to Earth to be caught and lowered down. The tethers could shorten trips between big planets from 9 months down to 5 or even 3, and reduce the scale of the rockets required by between 84 and 96%. Even better, people may be able to travel in relative luxury, as we could afford to invest in passenger comfort. Tether travel would be first-class seats to Mars. Together, tethers around Earth and Mars provide the rapid and cost-efficient transportation backbone that would make space travel affordable. But let's go further. Starting from low Mars orbit, a tether could boost ships to the asteroid belt. The first craft sent to a new asteroid would need rockets to slow down at its destination. Subsequent arrivals might find a tether waiting to catch them and send them back for free. Getting to asteroids cheaply is a major factor in opening up the resources of the solar system. Precious metals and valuable minerals could be delivered to Mars just weeks after they were cut out of their asteroid. They would be the perfect building blocks for our interplanetary civilization. But why stop here? Mars moons aren't very important. No other moons in the solar system orbit that close to their planet. Phobos is so heavy that we don't need to worry about slowing it down, making it the perfect attention point for super tethers just under 6,000 kilometers long. The lower tip would fly just over the surface of Mars and be very easy to catch. The upper tip can fling ships all the way to Jupiter and Saturn. The same super tether can also bring the inner solar system closer. Venus and Mercury are a single swing away. Unlike Mars, they're bursting with solar energy and are rich in minerals. In the long term, nothing is stopping humanity from constructing a zero-propellant transport network for the terrestrial planets centered on the Martian moons. Tethers are a comparably cheap and sustainable solution to making space travel affordable and the rest of the solar system accessible for exploitation and exploration. Considering that we have the technology to build them today, there's really no good excuse to wait anymore. Parts of the solar system are far away, but they could be very close. Speaking of stuff that's hard to reach, but doesn't have to be, knowledge. Our friends from Brilliant can hook you up to a universe full of explosive ideas and fun courses. Brilliant is a website that helps you tackle things in a practical way with interactive problem-solving courses and daily problems in maths, logic and engineering. Each problem gives you all the tools you need to crack complex topics all by yourself. It's learning by doing, but with your brain instead of your hands. Use your curiosity to get to the bottom of puzzles and courses about things like classical mechanics, astronomy, gravitational physics, and much more. If you click the link in the description or visit brilliant.org/nutshell, you can sign up for free and learn more things than you can imagine. And there's an extra perk for Kurzgesagt viewers. The first 688 people to use the link get 20% off their annual membership, which lets you view all the daily problems in the archives and unlock every course. Brilliant helps you end your day a little smarter. You might get hooked on the experience. Casually watching a video on YouTube seems more powerful than anything humanity could build a few decades ago. This progress and all the wonderful machines you take for granted are built on a few rare and precious materials with names like terbium, neodymium, or tantalum. Getting these rare materials from the ground into your devices is ugly. The mining industry is responsible for air and water pollution and the destruction of entire landscapes. Dangerous chemicals like cyanide, sulfuric acid, or chlorine are used to extract the resources, harming biodiversity, workers, and locals. And rare resources are also political tools when countries restrict access to them to get their way. But what if we could replace the mining industry on Earth with a clean process that can't harm anyone? Well, we can. All we need to do is look up. Asteroids are millions of trillions of tons of rocks, metals, and ice, leftovers from the cloud that became the planet 4.5 billion years ago. They can be as small as a meter, or protoplanets the size of entire countries. Most of them are concentrated in the asteroid belt and the Kuiper belt, while hundreds of thousands more do their own thing between the planets. As space travel is becoming more feasible, scientists and economists have begun looking at the resources found in these asteroids. Even relatively small metallic asteroids may contain trillions worth of industrial and precious metals like platinum. And bigger asteroids like 16 Psyche could contain enough iron nickel to cover the world's metal needs for millions of years. At current market prices, the rare raw materials alone would be worth quadrillions of dollars. Well, not really, but technically. For example, there are more than 20 million tons of gold in the ocean's water, worth roughly 750 trillion US dollars. But filtering out the gold would be so expensive that you'd lose money selling it. Right now, asteroid mining has exactly this problem. It's too expensive to replace mining on Earth. Billions of dollars worth of valuable resources in space are worthless if it costs trillions to get them. What makes it so hard? The principles behind mining an asteroid are simple. The basic idea is to choose an asteroid, move it to a place where it's easy to process, and then take it apart to turn into useful products. Unfortunately, all of this collides with fundamental problems humans have yet to solve. Going to space is expensive. It costs thousands of dollars in rocket fuel for each kilogram just to reach a low Earth orbit. Going further out into deep space costs thousands more. We need cheaper space travel to make asteroid mining profitable. One solution is to switch from classical rockets to electric spaceships. We already use electrical rocket engines for many of the space probes on science missions. In principle, we only need to build bigger ones. While electrical engines are not powerful enough to fly to space, they require only a tiny amount of fuel to go very far once they're in space. This means we don't need to spend a lot of money on fuel, only to transport fuel into space. This doesn't solve the whole cost problem, but it makes it easier to start our first mission. Now that we have an electric asteroid mining spaceship, we need to find the right asteroid and get it there. We've already successfully visited asteroids with space probes and even collected samples. Still, to make it easier and cheaper, our first targets will probably be near-Earth asteroids. Asteroids that orbit right near Earth. After a few months of travel, our spaceship finally arrives at an asteroid. Weirdly formed, littered with small impact craters, it hasn't changed much for billions of years. The first thing that needs to be done is to secure the asteroid and stop it from spinning. There are multiple ways to do this, like vaporizing material with a laser or stopping the rotation with thrusters. Once we have a stable asteroid, we need to wait. Orbital mechanics are complicated, but if you push something in the right direction at exactly the right moment, you can move very big things with very little force. So, we wait for exactly the right moment. Our ship fires its thrusters and nudges the asteroid into a trajectory that takes it near our moon. The moon is useful because we can borrow its gravitational pull to put the asteroid in a stable orbit around Earth, which saves even more fuel. Again, the trip takes months, but all the time since our ship was launched has not been wasted. The first space mining and processing equipment has been installed in orbit and is now carefully moving towards the asteroid. The processor works very differently than on Earth. Giant mirrors focus sunlight and heat up asteroid rock to boil out the gases. Grinders break up the dried rocks into gravel and dust, and centrifuges separate dense from light elements. Even if we only extracted 0.01% of the asteroid's massive pressure levels, this is still several times more than you get from sitting or on the ground. But what now? How do we get our safely back to Earth? There are a few ways, and loading it in, we need to return to Earth. Processor contains 3D printers system. Heat shield
Barely stop.